Today we're going to be talking about angular momentum and the conservation of angular momentum. Every moving object has angular momentum, but it's always referenced to a particular axis of rotation or revolution. That is, some point around which an object is moving. Even if an object is moving in a straight line, it has angular momentum with respect to some other point in space. The choice of that other point in space, the axis, is sometimes arbitrary and sometimes it's natural. In this case, we're going to illustrate angular momentum with a rotating platform and Meghan, who will step up on the rotating platform. And the axis of rotation in this case is quite clear. It's the axis of this platform that Meghan is standing on, that she can spin around. Now I'm going to have Meghan stick her arms out so it's easier for me to push her around and make her a little bit sick to her stomach, perhaps. In order to change the angular momentum of a system, you have to apply a torque. A torque is a twisting force. If I apply a force to Meghan in this direction, there's no rotation. I'm applying a force but not a torque because the force vector that I'm applying goes through the axis of rotation, which is vertically through the platform. So there's no distance between that force vector and the axis of rotation. However, if I apply a force this way, the force vector is going towards you, towards the camera, and it has a distance equal to the length of Meghan's arm from the axis of rotation. That's called the lever arm. So in this case, the force is applying a torque. That's the product of the force and the lever arm. When I apply that force, I've changed the angular momentum of Meghan, and she's now turning. She now has a certain amount of rotational or angular momentum that will stay the same until some other torque acts on the system to change it. So if I apply another torque this way, that stops her rotating. I apply a new force, a new twisting torque to bring her back to this orientation. Now I'm going to start Meghan rotating again by applying a torque. The only other force, twisting force that's acting on her is friction in the turntable. So I apply that torque. She'll keep this conserved quantity of angular momentum until the torque due to the friction in the turntable causes her to stop. If she pulls her arms in towards her body, you'll notice that she's spinning faster. Pushes her arms out again, she slows down. Her angular momentum is not changed in that case. The angular momentum was constant through that process. You can lower your arms. But some other aspect of Meghan changed, and that is her moment of inertia. Moment of inertia is a description of how mass is distributed relative to an axis of rotation. So when Meghan puts her arms out, she increases her moment of inertia by increasing the distance of mass from the axis of rotation. And when the moment of inertia is large, not as much rotational velocity or motion is needed to have the same angular momentum. This will be easier to see if we give a little extra mass to Meghan. So she's got two 5-pound masses here. She's an athlete. She can handle it with raised arms, no problem. So now she's got a higher moment of inertia than she did before. I apply the torque. She has angular momentum, and she can bring her arms in, and she spins up much faster. She wisely puts her arms out. Angular momentum was constant throughout that whole process, but the rate of rotation isn't. That's because angular momentum is a product of the rate of rotation in angular velocity times the moment of inertia. When her arms are out, the moment of inertia is large and the angular velocity is small. When she brings her arms in, the moment of inertia gets small, so her angular velocity must increase. She can change her moment of inertia just by moving her arms, so she can control her angular velocity by adjusting her moment of inertia. There are no external torques acting during this whole process, so throughout it all, her angular momentum is constant.